Well, now let's take a look at an example of a class of functions, all of which are uniformly continuous. For a line, y equals mx plus b, or f of x equals mx plus b, the slope-intercept form for the equation of a line. The changes in y, the changes in the function value, the height, relative to the change in x, is constant. The changes are constant, depending only on the slope m, not a particular value of x. So if the slope is 2, or 2 over 1, and for x equals 7, if you move one step to the left, or greater than 7 to 8, the value of the function is going to go up by 2. If you're at x equals 100, and you increase by 1 to 101, the height of the function, or value of the function, is going to increase by 2. Exactly the same thing. Doesn't matter where on the x-axis you are. Take one step bigger, the height of the function is going to increase by 2, assuming that the slope is 2. Well, this theorem just says that the function this is uniformly continuous. All lines that are functions, doesn't include vertical lines, but all other lines are uniformly continuous. And let's prove that. You may want to have the definition out in front of you as we look at this, since I had to erase it. Well, first of all, we need an epsilon. Let epsilon greater than 0 be given. And now I have to choose a delta, but I don't know what I want to choose yet. So I'm just going to say let delta equal something. We'll fill it in later when we figure out what it needs to be. Okay, so for any two values in the domain that are closer together than delta, less than delta distance apart, we want to show that the values of the functions at those two values, value of the function at that x and y, say, when you take the difference, is less than delta. And it doesn't matter which two values you pick, as long as their distance apart is less than delta. All right, so let's just say thus, and here is where I'm saying this is, and I don't have to say x and y being in the domain in this case, because the domain is all real numbers. So for any two real numbers, x and y, if they're closer together than delta, then, and let's figure out what f of x minus f of y is. As soon as we can prove that that's less than epsilon, we're done. Well, that's going to be equal to, what's f of x? Mx plus b. Minus my plus b. And to save some room, I think I'm going to keep going left to right because I've got a little bit more I want to write after this theorem. Oops, absolute value. And what does that simplify to? Well, I can see that the b and the b's cancel out. So that's just going to leave me with mx minus my, which I'm going to distribute. Okay, I did a couple things in that step. If you don't like that, then work it out yourself. This simplifies in the absolute value to be mx minus my, and I factored the m out, m times x minus y, and the property of absolute values allow me to make this statement. Okay, well, actually, we're almost done. What do we know about x minus y at absolute values? It is less than delta. So this is less than m delta. If I make epsilon equal to m delta, we're done. And I'm going to force it to be that. Now, what does that mean? M delta equals epsilon. Well, that's true if and only if delta is epsilon over absolute value of m. That is what I'm going to put in this box. And that completes the proof. Simple as that. Okay, a couple other, I'm going to rewrite the definition that we just used, and then on occasion you're going to have to prove that a particular function is not uniformly continuous. So I'm going to negate that definition as well. So I'm going to say, we just did this, but recall. F uniformly continuous on capital D means if uniformly continuous. For every epsilon greater than 0, there exists a delta greater than 0 such that if x and y are in the domain and they're close together, x minus y in absolute values is less than delta, that implies that f of x minus f of y in absolute values is less than epsilon. And something similar to what I mentioned earlier, I could have put a for all x and y in the domain with this happening. For every single pair x and y in the domain where this is true, that implies that this is true as well. So I'm going to say it follows that I'm going to change this definition. F is not uniformly continuous on D if, all right, so now I need to negate the definition that we have right here. This is the one where I used only symbols to define it, but it's nice, short, and sweet that way. All right, how do we negate a statement like this? Well, remember that whenever you have a for all epsilon greater than 0, something happens. To negate it, all you have to say is there is one where it fails. So remember, the for all turns into there exists an epsilon. When you have there exists, it turns into for all. Okay, so the negation will be there exists a delta, an epsilon greater than 0 where all that fails. So it doesn't work for all the epsilons. I'm going to find one where it doesn't work. There exists a delta is going to be, for this epsilon, I cannot find a delta to work. For all delta greater than 0. And now I need to negate all of this. And I put that for every up there for to make it easier for us. This says for every x, if this is true, that's true. I've got to find an x and a y in the domain where that's false. And before I write that, notice that this in parentheses is like a P implies Q. If this is true, then this is true. This would be the P, this would be the Q. Hopefully you remember what the negation of that is. And you remember what the truth table looked like? There's only one way to make this false. You make the premise P true, and you make the Q, the conclusion, false. So I'm going to say, make this true. There exists an xy here, but, or and, this is greater than or equal to epsilon. So there exists an xy in the domain, and their distance is close, less than delta. And I'm going to put but here as well in parentheses. But f of x minus f of y in absolute values is greater than or equal to epsilon. That is the negation. This for every x and y turned into there exists one where it fails.